Good morning and welcome to the KE webinar for 13th of November 2019, and today we're looking at learning lessons from structural failures. My name is Adam and I'm the Regional Services Coordinator here at CABE, and I'll be acting as moderator for this morning's session. We like to make our webinars interactive, so we do encourage you throughout the session to send in any questions as we go along, which we will address with a Q&A at the end of the presentation. So to get in touch with us, you can type in questions. There's a little panel on your screen that should be either on the top side or to the side of the screen, depending on how you're viewing this session today. Just go to the question panel and then type in any questions. These will appear on my screen, and then once we get to the end of the presentation, I will look to go through the questions with Paul. If we get lots of questions, I may not have time to address them all, but what we can do is forward any unanswered questions to Paul outside of this morning's session. If you're watching via YouTube, you can still ask questions, but please just send them to info@cbuilde.com. And if you're on Twitter, you can chat to us using the hashtag KCPD. So this morning, your presenter is Paul McNulty. Paul is a senior engineer with structural safety. He has design and assessment experience in civil and structural engineering, including completing a PhD on an innovative arch bridge design, working in consultancy as a structural engineer in both the offshore oil and gas industry and the onshore buildings industry. He has a particular interest in safety and enjoys promoting the best practices from his experiences of working in both industries. So if you give me a couple of seconds, I'll hand over to Paul and he'll take control and take you through his presentation. Brilliant.
Okay, thank you, Adam, and good morning, everyone. Firstly, thanks to CABE for inviting us to give this webinar this morning, and thanks to everyone who's got up so early to listen in. So my name is Paul. I work as a senior engineer with structural safety, and for this talk on learning lessons from structural failures, I'm going to discuss the work that structural safety do, and including sharing lots of examples of different safety issues that we come across that you can hopefully all learn from. I'll probably talk for about 45 minutes or a little bit less, and as Adam said, I'm happy to take any questions at the end. So firstly, just a little bit of background to the setup of structural safety. We have three sponsors, so they are the Institution of Structural Engineers, the Institution of Civil Engineers, and the Health and Safety Executive. So we don't have any commercial funding from the industry, which is very important, as that helps to keep us independent from any commercial influence in the industry. And the name Structural Safety is a group that has two parts, which are SCOSS and CROSS. So the first part is SCOSS, which stands for Standing Committee on Structural Safety, and it was set up quite a long time ago in 1976, and their role is to really maintain a review of the building and civil engineering matters that affect safety, and they do this by following this very simple process. So firstly, we collect data from any public sources on structural failures. So that's really all the failures that you hear about in the news. We then analyse all that data and we decide if there's any unacceptable risk in the industry or if unacceptable risk might arise in the future. And if there is any unacceptable risk, we then publish safety alerts. And most of the time, the safety alerts are really to raise awareness of that risk so that people can manage that risk. We're not always able to provide the answers to the risks all the time, so most of the time it's just really about raising awareness of the risks. And this slide here shows some recent safety alerts that we've published. So top left was a very severe fire at a multi-storey car park in Liverpool at the end of 2017. So there was about 1,300 cars went on fire during this fire. And interestingly, the fire design for car parks is based on the theory that the fire will stay in one car if it goes on fire, but it won't jump between cars. But in this instance, the fire did jump between cars, and it jumped between levels in the car park. And by the time the fire service got to the car park, the fire was already badly out of control. So it's a good example of how a design philosophy can be breached, and the catastrophic consequences that can have. Top right is the collapse of a steel frame building in London in 2012, and I'll speak about that in the next few slides. Bottom left, I'm sure most of you know about this already if you're UK based. It's the collapse of the outer leaf of a cavity wall at a primary school in Edinburgh. And again, I'll touch on that in the later slides. And bottom right is our most recent safety alert, which is about the failure of RAAC planks, which stands for reinforced aerated autoclaved concrete planks. And these were a form of construction that were used in the 60s and 70s, mostly in schools. And recently, there's been some safety issues with these planks. Okay, so this is the steel frame building in London, which collapsed in 2012. So as you can see, it's a braced steel frame, and it was a religious building. So one of the design requirements was that they wanted to have a column-free zone at first floor level for large congregations. So this is one of the design drawings. So in order to achieve this column-free zone, if you look at roof level, you can see that there's a floor deep truss that spans from the front of the building to the back of the building. So it's a 36-metre long span truss, which is a floor deep. And then the red vertical elements, they are tension hangers that were welded to the bottom of the truss. And the tension hangers then supported the third floor, that's shown in blue. And that then allowed the column-free zone below the third floor in blue. So, you know, it's definitely not your standard steel frame building design. Something a little bit different, and something that's a little bit more risky than a normal design. And then the whole thing catastrophically collapsed. And this collapse happened about 15 minutes after the workers left site that day. So although there were no injuries or fatalities, it definitely was a near miss and could have been much, much worse. So the HSE did an investigation into this collapse, and they were able to share the investigation report with us, and we then produced a short safety alert on it. So there were two main technical causes to the collapse. Firstly, on the left, you can see that there was defective site welding of the hangers to the truss. So just as a reminder, these are the tension hangers that were hanging off the bottom of the truss to support the third floor, and the welding was of poor quality. Then on the right hand side, at the bottom of the tension hangers, there were gusset plates which were then welded to the third floor beams. But when the contractor on site went to bolt these gusset plates to the third floor beams, the bolt holes weren't lining up properly, so they re-drilled the bolt holes, which is shown as the red holes on the right. And for all you structural engineers tuning in, you'll then know that significantly reduces the shear capacity of the gusset plate along the line of the bolt holes. So what's the main lessons to be learned from this collapse? The first one's about robustness. So again, all the structural engineers tuning in will know that structures should be designed to be robust so that a local failure does not cause disproportionate collapse. So one of the theories about why this collapse might have been so catastrophic was that one of the tension hangers failed, and that then overloaded the adjacent tension hangers, and then you get a zip effect of all the tension hangers failing. And that just shouldn't happen, because post Ronan Point, now that we have part A3 of the regulations for disproportionate collapse, structures should be designed to be robust to prevent this kind of failure. And the second point here is that if you're designing any tension structures, always try and design them to have some sort of ductility so that you can get warning of failure. The second lesson is about the importance of connections. So on this project, they decided to weld what was a very safety critical connection. Our advice would be to try to avoid site welding if you can. Go for bolts or off-site welding where it can be done in a more controlled environment. But if you have to do site welding, then you've got to follow the procedures very carefully, and that's everything from preparing the surface to getting the right qualified welder, to implementing the weld, to testing the weld, inspecting the weld, approving the weld. There's a whole host of procedures that have to be very carefully followed. Interestingly, one of the HSE's recommendations on this project was that the structural engineer could have specified 100% inspection of these welds because they were so safety critical. And then the second point on connections is that contractors should not be amending any design on site without going back to the original designer first of all. And the third lesson from this incident is that designers should always be trying to make contractors aware of risks involved with unusual structures. And although that seems fairly obvious, it can be quite difficult sometimes, especially if you're a designer and you're working on quite a large project. You become very familiar with the project. Risks might seem very obvious to you, but in that case, you have to think, would a contractor who's only looked at your drawings for an hour or two, doesn't understand your design in as much detail, would they appreciate the risks? Maybe not. It might be a good idea to get a colleague who works in your office that hasn't been involved in the project at all to take a look at your drawings and see do they spot the risks which you think are quite obvious. Okay, so this is the Edinburgh Schools wall collapse. So it was a gable end wall that collapsed due to a wind suction load. So basically you've got the wind coming along the length of the building, and then when it gets to the gable end, it then causes suction on the gable end wall. So 9 tons of masonry collapsed here. And again, similar to the last example, this was a real near miss because this was a pathway that kids used to walk into school every morning, and this collapse happened a few hours before the kids would have been there. So again, a real near miss. So the Scottish government did an inquiry into this collapse, so it's a publicly available document that you can find online. And like any collapse, there was a whole host of issues that combined together to cause this collapse. But one of the main causes was that there was an inadequate tying of the inner leaf to the outer leaf of the cavity wall, and I'll explain why that happened in the next few slides. So typically if you're building a cavity wall, you'll build the inner leaf and the outer leaf together. You'll put your wall tie in and you'll keep building the wall. So there's no real safety risks there. It's a fairly simple process. But on this project, they were running behind on program, so they wanted to try and save some time on program. And to do this, they decided to build the inner leaf first, because that then allows you a watertight building, and the follow-on trades can then start to work on the inside of the building. So they built the inner leaf, they put the wall tie on, but it's pretty clear that the wall tie isn't balanced in that state because there's no outer leaf there to balance the wall tie. This is only a problem if you've got the heavier wall tie types. If you've got the lighter wall tie types, this won't even be an issue. But if you've got the heavier wall tie types, the wall tie will fall over. Now, it's not really a big issue. There's a lot of solutions here. You could hold the wall tie in place while you put the next block on top of it to stabilize it. You could get longer wall ties. You could mechanically fix the wall tie to the block. But the brickies on this project were getting paid per brick or block. So the quickest thing for them to do was to move the wall tie inwards so that it was balanced on the inner leaf. And that then meant when you go to build the outer leaf of the wall, you don't have your minimum 50 millimeters embedment anymore. So it should be pretty obvious then that when a wind suction load comes onto this here wall, it's going to pull the outer brick leaf down, because it's effectively acting by itself with very little or no support from the inner leaf. So not all of our safety alerts are about incidents that happen. This is one of our more recent safety alerts, which is more looking into the future, about future risks that we see arising in the industry. And this particular alert was prompted by concerns that were raised directly to SCOSS about some particularly large structures. And as the quote here says, this topic is gaining in importance as clients and their designers strive to build lighter, bigger, taller and longer. So the alert discusses several topics. One of them is long span steel beams, where the rotational demands at the end connections are proportional to span cubed. So SCOSS feel that it's questionable whether industry standard detailing rules remain valid for such long span steel beams. For example, if you have a very long span steel beam that's designed as simply supported, but there's very high end reactions that require a large number of bolts with very deep connections, then that connection might behave more like a fixed end connection as opposed to a pinned end connection. General effects of deflections are also discussed, where deflections due to tolerances combined with bending can lead to in situ concrete slabs being much thicker and therefore much heavier than designed for. So this is the case if obviously a beam is going to bend downwards, and if the tolerance is also downwards, then you can get this situation arising. And this is especially a problem if the slab is designed to be installed level as opposed to a constant thickness, because if you imagine at mid-span of a beam, the beam's bending and you want to put more concrete in to get the slab level, that's just going to add more load to the beam at mid-span, which is going to cause it to bend even further. So the alert also discusses steel thicknesses, where it doesn't seem to be uncommon now in projects to have steel thicknesses of over 100 millimeters. And the danger here is that designers might be moving into a territory that they might not have much experience in, so they might overlook some key technical issues, such as the fact that thicker steel is less homogeneous, so it's more prone to lamination, or becomes more vulnerable to through thickness cracking. Now, these are things that you can design for, but you can only design for them if you know that that risk is there. And then similarly for welding very thick steel, thicker steel requires more care in welding, since the cooling rate of weld beads is linked to the thermal conductivity of steel, which in turn is linked to the thickness of the steel. So the welds in thicker steel will cool quicker, so they might become hard and brittle, and therefore they might not meet the ductility requirements. But again, if you're aware of this, then you can manage it by either applying specialist welding procedures or post-welded heat treatment. So again, if you go onto our website, you'll find all of these safety alerts, which are free for anyone to read. Okay, so that's SCOSS. So just as a recap, SCOSS are looking at everything in the public domain. The other part of structural safety is CROSS. So CROSS stands for Confidential Reporting on Structural Safety, and it was set up in 2005 with the role of really capturing and sharing lessons learned from safety issues which might not otherwise have had formal recognition. So basically, the thinking at the time was that it's very good that SCOSS are looking at everything in the public domain, but there's a huge amount of stuff that happens below that never makes it into the public domain. So they decided to set up CROSS as a mechanism for the industry to submit reports and share and learn lessons from each other. So this little flowchart here shows the process that we go through in CROSS. So the first stage is that we receive a report, and as I said, all reports come from people who work in the industry, so mostly engineers. And the reporters always tell us about a safety issue. So it's not always a safety incident that's happened. Sometimes it's just a safety concern that they might have, or it could be a minor incident. So stage 2 of this process is that we then process the report. And there's 2 parts to this. Firstly, we remove the reporter's details. So there's a very small number of people that ever get to see the reporter's details. And we also remove any identifiable details from the report because we're not interested in blaming anyone or anything. So we remove any reference to a project or a product or an individual or a company. All that we're really interested in doing is sharing the technical lessons to be learned from that report. So at the end of this stage, the report's now completely anonymous, and it then goes to our CROSS panel, who are a range of experts in their respective fields across the industry. And they read the report, they discuss why that safety issue happened, and they then write a few short paragraphs summarising what readers can learn from that report. So very often it's links to guidance documents or codes of practice that should have been followed. So the 4th stage is then the reports are all published on our website, free for everyone to view, and the best reports make it into our quarterly CROSS newsletter, which if you're signed up to our mailing list, you'll get an email about that newsletter every 3 months. And then the last stage, and probably the most important stage of the whole cycle, is that the whole system is designed to try and influence change and improve safety in the industry. And this can happen in several ways. Probably the most popular way is if you read a CROSS report and you can apply the learning from that report to the projects you work on. That can only be a good thing for safety. We also have a lot of close ties with different professional industry and trade bodies. So if we notice any trends in our reports, then we'll try and work with them to maybe issue some guidance documents. So as I said, every 3 months we publish a CROSS newsletter, which really includes a selection of the most relevant reports which we've recently published. And if you're signed up to our mailing list, then you'll receive an email when we publish a CROSS newsletter. Okay, so I'm going to talk you through 1 or 2 CROSS reports now, just to show you the benefit of the scheme. So here you have a train running over rail tracks, and you can see that there's a very large steel signal structure cantilever over the rail tracks. Now, you don't need to be an engineer to realise that if that structure collapsed, it could have very severe consequences. It could easily cause fatalities if it hits a train. So we received a CROSS report that had a safety concern about the base of one of these structures. And bear in mind, they only have one base. If that base fails, then the structure will collapse. So you can see a picture of the base on the right. And the reporter said that 5 of the 12 holding down bolts had failed. Of the remaining 7, 6 of them were severely damaged. So a single nut on one bolt was holding the entire structure from collapse. And the reason that it had got into this state was that the designer had specified that grout was to be installed between the concrete plinth and the steel base plate, and the contractor just never installed it. And that grout, there were several reasons why it was required from a design perspective, but in this case, probably the most important reason was that it encapsulated the bolts, so prevented any water getting to the bolts and corroding the bolts. So because the grout wasn't there, the bolts then were severely corroded. So the CROSS panel's comments in this report, they were actually fairly simple. It just said that given that the consequences of failure of this base were so high, then its construction, including the site supervision, inspection and approval, should have merited special attention. And that's a very good lesson that you can apply to lots of projects. So for all the projects that you all work on, what systems and procedures are in place to make sure that safety critical elements and connections are actually constructed in accordance with the design. And the very interesting thing about this report and the vast majority of cross reports is that because there was no collapse, so it was very close to collapsing, but it didn't collapse, and therefore there were no injuries or fatalities or any major disruption to infrastructure. This doesn't make it into the news, but I think from an engineering perspective, there's some really key lessons to be learned from reports like this, and that's why it's great that we have Cross there to do that for us. So this is another cross report on rotting of cross-laminated timber roof panels. So this report was published in our newsletter last month, and it has received a lot of interest. So the reporter in this case was asked to check the roof of a building which had been leaking for a few years but was still occupied. So the roof consisted of flat CLT panels with falls provided by furring pieces with insulation and supporting marine ply under a single ply membrane. So during the reporter's inspection, they found that in some areas 3 of the typical 5 plies in the CLT panels had rotted through both on parapets and roof panels. They go on to say that the remedial work consisted of replacement of the flat roof areas using parallel cord timber trusses with metal webs. So the cross panels comments for this report focused on how the water could have developed, which they speculate could have been due to condensation or leaks in the waterproof membrane. And they included links to a British standard on controlling condensation in buildings, as well as BRE papers on CLT and thermal insulation. So if you want to read this report in full, just have a look at our latest newsletter on our website. So I hope those explanations of SCOSS and cross make sense, and that's provides a bit more clarity. So this diagram here shows a pyramid of risk for safety incidents, just to give you an understanding of where structural safety operates in this pyramid. So at the bottom, you've just got your normal operations. Well, there aren't any safety incidents, but there might still be safety concerns. An example of this level might be if you find out that a steel fabricator is producing non-CE marked steel. And then gradually, as you move up the pyramid, things get more and more serious, and at the very top, you get safety incidents where there are fatalities. So no one's going to come to cross the confidential reporting scheme with safety incidents at the top of this pyramid. The police or the regulatory authorities are going to get involved first, including maybe the HSE. And after they've done their investigations, they then might share some of the data with us so that we can share the learning from that incident with the industry. But we're never going to be the first port of call there. Cross the confidential reporting scheme, it's very much focused on the lower levels of this pyramid, and very often the stuff that doesn't make it into the news. Now that might seem unusual that we've decided to focus on safety concerns and incidents that don't cause major injuries or fatalities. But there's 2 reasons why we think it's important to focus on these lower levels. Firstly, you very often find that there's a lot more data at the bottom of this pyramid than there is at the top. So every time there's a major incident in the industry, when you start to speak to people, people start telling you that they worked on a project where that almost happened, or they had a concern about that type of incident happening. And so basically there's quite a lot of data out there to be gathered before the major incident happens. And secondly, we do a lot of analysis on the cross reports that we have, and we categorize all the reports to a defined taxonomy. And we very often find that the safety concerns and incidents at the bottom of this pyramid have precursors for the incidents at the top. So if we can identify those precursors and address them, then we can hopefully prevent the more serious ones at the top of this pyramid. So we have a SCOSS committee and a cross panel, probably about 20-25 people altogether, mostly engineers from all different fields and industries. Contractors, we've got a government representative, HSE, Highways England. So a lot of the major players are involved. We even have a solicitor who reviews all of our work before we publish it, and then we have a few young members there as well. So we've received almost 900 cross reports now in the last 15 years. And this chart here shows at what stage of the project that the root cause of the safety issue is. So it's not necessarily when it happened, it's what stage the root cause is. So for example, you might get a collapse that happens during construction, but if that was caused by a poor design, then it would fall into the design category of this chart. So it's pretty much a third construction, a third design, and a quarter operation. But it's worth bearing in mind that most of our reports come from engineers who aren't always involved during the operation stage of the project. This chart here shows during the design stage what the actual root cause is, and half of the time it's inadequate design principles, which is just general errors in the design or analysis of the permanent works. 18% of the time is due to inadequate detailed design, so that's design of anchors, fixings, connections. You know, that's quite a lot of reports, probably over 150 reports fall into that category. It just seems to be in projects that there's a lack of understanding with who's responsible for connection designs. Maybe they're not the most exciting thing to design, so people get a little bit bored doing the designs and don't do the designs properly. But it's a real area of concern for us. So there's the same chart now, but during the construction stage. And here, pretty much a third of the time is due to inadequate competency of the contractor. So that's just appointing a contractor who didn't have the right skills or experience to conduct the work. 17% of the time is due to inadequate quality assurance, so that's either a lack of or no site inspections to make sure that the contractor is actually building the structure to the design, or if the contractor has their own self-certification system in place, then it means that that system wasn't robust enough. For example, if you go back to the Edinburgh Schools example, the Scottish Government inquiry report states that they had all the quality assurance sheets signed off, but they didn't provide real evidence that the work was conducted properly. So an example of providing more robust evidence would be to actually have photographs of how you installed all the safety critical elements. So again, there's a lot of reports, probably touching 200 reports fall into that category. And it really begs the question that all designers and clients should be asking themselves, which is what I thought was going to be built actually what was built? 16% of the time it's due to poor communication during the construction stage. So this is really poor communication between all the parties involved during construction. This is probably the section of the chart which has risen most in recent years, and we think it's maybe because of design and build contracts where there's more organisations involved during construction, and the more organisations you have involved means the more communication interfaces you have, and the more communication interfaces you have increases the probability of communication errors happening. So as I said, we try to look for trends in our reports and then take action on those trends. So fixings and connections is a trend. So on the left was the collapse of a ceiling, of a suspended ceiling in a cinema. So it happened overnight, so again, a near miss. And here they used lightweight fixings to connect the ceiling to the slab above, but it wasn't a lightweight ceiling at all. It was 50mm thick plasterboard with quite a lot of services, so it just wasn't taken very seriously. On the right, this was a steel angle that was being bolted to a reinforced concrete core, and that steel angle was then going to support precast concrete stairs. But when the contractor went to bolt the steel angle to the core, the bolts clashed with reinforcement in the core, and instead of just taking the bolt out and moving it 30mm to the side to avoid the reinforcement, they tried to angle the bolts to miss the reinforcement, so just really poor construction practice. And this slide here then shows how the precursors from cross reports can lead to major failures in the industry. So in all three of these examples, tunnel linings collapsed due to the failure of epoxy anchors. So these are not cross reports, these are all incidents in the public domain that cost a lot of money to fix. But if you look at the root cause of why these incidents happened, it's the exact same as the root cause of some cross reports. So if people were able to read and learn from the cross reports, then they could potentially prevent major incidents like this happening in the industry. So we issued a SCOSS alert in 2010 on fixings. In the same year, the Construction Fixing Association issued guidance. There's a British standard there for fixings now. And literally a few months ago, Surrey released really extensive guidance documents on the selection and management of safety critical fixings. So there's quite a lot of good information out there now. Another trend that we came across was stability. So here you've got a temporary structure, a little stage. And it's a very top-heavy structure, so all the mass is on the roof. So you've got the weight of the roof itself, you've got the lights and the speakers hanging off the roof. So it's all, so as I say, it's a very top-heavy structure. It's almost like an inverted pendulum, which is inherently unstable. And there doesn't seem to be any vertical stability system. So there's no vertical bracing. There doesn't seem to be any rigid connections. Now, there was no collapse here. They've probably just got a little bit lucky. Maybe it wasn't a very high wind load, or maybe they got some sort of fixity in the connections at the top. But the warning signs for a failure are definitely there. And around the same time, we received a cross report about another temporary stage. This time there was a stability system. They used water tanks connected to the stage by straps. But there's a whole host of issues here. Firstly, the straps aren't even tensioned. Secondly, the tanks aren't anchored down to the ground. So if it's a wet day, the tanks might just slide along the wet grass because the coefficient of friction will be low. And thirdly, water tanks just isn't a very robust solution, because if someone punctures a water tank, then you've lost your stability system. But again, no collapse, but the precursors for a collapse are definitely there. And then about a year after we received these reports, a stage in Indiana collapsed during a concert, where 6 people were killed during the collapse. And the stability system here was actually quite similar to the last example of water tanks, but instead of water tanks, they used concrete blocks, which is more robust. But the designer had specified that the concrete blocks were to be placed on top of concrete. But then when they started to install the little marquee shown in white around the main stage, these clashed with where the concrete blocks were meant to be. So some of the concrete blocks were actually placed on top of grass instead, which has a lower coefficient of friction. So the blocks slid along the grass. So again, we issued a safety alert on this. And that safety alert was used as part of the check-in procedures for the 2012 Olympics in London, which had a really good safety record. And the IStructE have an excellent guidance document on temporary demountable structures as well. So again, there's a lot of good information out there on that topic now. So tower block tragedies, Roland Point, for all the structural engineers tuning in, you'll be well aware of Roland Point. So 1968, there was a small gas explosion at the top of this tower, and it caused the external wall to pop out, and the slabs above then fell down onto the slabs below, and you had a progressive collapse of the corner of the structure. And the thinking at the time was that the damage caused was actually disproportionate to the initiating incident. And that is where part A3 of the building regulations for disproportionate collapse came in. So the point of showing this slide is to say that you never want something like this to happen, but the positive is that the industry reacted by improving legislation so that going forward structures will be designed to be more robust. And then on the right you've got Grenfell Tower, the ramifications for which will change how the risk of fire is managed for tall residential buildings. So what does 60 minutes fire resistance mean? I added this slide in probably well over a year ago. I attended a lecture from Colin Bailey. It was his inaugural lecture for becoming president of Queen's Mary University of London. His lecture was on collapse of World Trade Center 7, which collapsed due to a fire. A very, very interesting presentation. So Colin was he's a structural engineer with a specialism in fire, and what I found very interesting was that he said throughout his career he's seen a lack of understanding of the behaviour of structures during fire from engineers. And he asked this question, and a lot of people didn't seem to know the answer. So I'm a structural engineer, and I thought I knew the answer to this question, and I didn't. So the two common misconceptions are that 60 minutes fire resistance means that the building will remain stable for 60 minutes, or that it will allow people to evacuate within 60 minutes. Very often both of those statements will be true, but that's not what 60 minutes fire resistance means. What it means is that the elements in the building will survive 60 minutes in a standard fire test, so it doesn't mean anything else. And that standard fire test follows a standard fire curve, so you get an element, you increase the temperature versus time, and you measure the load bearing capacity, the insulation, and the integrity. And if it passes that test, then it gets a 60-minute fire stamp. So the question then is, if all the so let's say you design a steel frame building, if all the elements in that building pass the 60-minute standard fire test, then why can't you say that the building's going to be safe to evacuate within 60 minutes, or that it's going to stand up for 60 minutes? And the reason why is because you're then making the assumption that the members will provide the same level of performance, i.e. behave in a similar way when they form part of the building. And Colin went through a whole host of reasons about why that assumption isn't valid. Some of the ones that I remember were that the test is always based on a 4.5 metre long member, so if you design members that are longer than this, then they'll behave differently during a fire. The test doesn't consider cooling effects, so if you heat up a steel beam, it expands and plastically deforms, and then when it goes to cool down again, because it's plastically deformed, it then shortens along its own length, which causes huge tension forces in the end connections, which may cause them to fracture. So the test again doesn't consider this. And the test is done in a very controlled laboratory environment, and maybe that same level of quality isn't met on site sometimes. So in summary, when you use the prescriptive fire design approach in the approved documents, it's worth remembering that that doesn't consider the actual structural behaviour of the building or the effects of real fires in buildings. And it's also probably worth bearing in mind that the approved documents are meant to be used for common buildings. So if you're working on a building which is very complex and deemed to be uncommon, then you should be considering adopting a performance-based fire design approach instead. The performance-based approach is more scientific, but obviously the design costs more, so clients might not want to go for it because they'll just want to meet the building regulations. However, I've been told that in many cases clients can save money during construction by adopting a performance-based approach, because in a performance-based approach you're only applying protection to the members which require protection, as opposed to applying protection to all of the members in a prescriptive-based approach. So it's just something to think about in the projects you work on. I think a good starting point would be to make sure that all the people in your organisations have a basic understanding of the behaviour of structures during fire, and also to appreciate that for complex or uncommon buildings, they should be considering doing a performance-based design for fire. So just back to Grenfell then, what are the government actions on Grenfell? So there's a public inquiry taking place, which was commissioned by the Prime Minister, which was Theresa May at the time, I believe, and that inquiry has been led by Sir Martin Mirbeck. So they published the phase 1 report a few weeks ago, and that was a factual narrative of what happened on the night of the fire. So phase 2 of the inquiry, which is probably of more interest to engineers, because it'll look at how the tower became exposed to the risk of the major fires. So it's going to look at the design, the construction and management of the building, including the refurbishment where the cladding was added to the building. So I believe that the hearings for phase 2 are expected to begin soon. And if you want to follow that inquiry, I'd highly recommend listening to the BBC podcast on it, which gives a short summary for every day that the inquiry sits. So the government also commissioned Dame Judith Hackitt to conduct an independent review of the building regulations and fire safety. And this review happened at a much faster pace. And Dame Judith published her final report in May last year, which included over 50 recommendations to improve the safety of buildings and to address what could be seen as evidence of systemic failings in the regulatory system. So what was her main findings? She found that roles and responsibilities for building safety were unclear, regulations and guidance are ambiguous and inconsistent, compliance with the regulations is weak and complex, competence of people in the system is patchy, product testing, labeling and marketing was also called into question. And even when residents do raise safety concerns, it was found that they very often weren't listened to. So Dame Judith then, as I said, came up with over 50 recommendations. And in summary, she's recommended that there should be a much tougher and stronger regulatory framework. And there should be a new building safety regulator, which would comprise of the Fire and Rescue Service, the HSE, and local authority building control. And she's also recommended the introduction of a safety case approach, which is just really a very structured and controlled way of managing risk, and in particular structural safety and fire safety risks throughout the life cycle of the building. And she also recommends there should be clear responsibilities to manage risks during the occupation stage of buildings. And one of her recommendations was that CROSS should be extended and strengthened to cover all engineering safety concerns. So since this report was published, we've worked with the government on this, and we're now planning to expand CROSS to cover fire safety issues as well as structural safety issues. And we're working closely with the Institute of Fire Engineers to bring that recommendation forward. So what's the likely consequences from all of this? There's going to be changes to the building regulations. So this has already started to happen, where approved document B for fire has went under consultation. There's already been changes to it, and there will be more changes. And other parts of the building regulations are also likely to follow. And as I say, there's going to be a more rigorous process for managing risk in high risk residential buildings. There's going to be improved competency all around, so all of the professional bodies have been meeting over the last year to 18 months to discuss competency requirements for working on these buildings. There's going to be stronger penalties for non-compliance. And as I say, there's going to be more safety reporting with the expansion of CROSS and the introduction of a mandatory reporting scheme as well as a voluntary CROSS reporting scheme. And it'll also be a requirement to have digital records for these buildings. Okay, so last few slides. We're in the process of setting up CROSS International at the minute, where there will be parallel CROSS schemes in other countries. And this is great. So basically other countries have seen the success of CROSS in the UK, and they want to have CROSS in their country too, which we're more than happy to help them with. So we already have schemes in Australia, Southern Africa, and a few months ago we launched in America, and Germany are planning to launch sometime next year. And the the long-term vision is that we'll have one big international database of all these cross reports so that we can all learn from each other across the world. So final slide, what's the benefits of confidential reporting through cross? So this is a quote from Eleanor Roosevelt, who's former First Lady of the US. So Eleanor said, "Learn from the mistakes of others, you can't live long enough to make them yourself." So a very wise quote. So submitting reports to cross helps us to identify safety trends. So these might be trends that you already know about, but you're not sure how widespread an issue it is. Or they might be new safety trends coming into the industry. As an example, recently we've been receiving quite a lot of reports about the failure of structural glass, so that might be a trend that we have to address. It's a proven system, so we have based cross completely on confidential reporting in the aviation industry, which has been very successful, so it does work. And we're not a regulator, we're not a whistleblower organisation. You know, no one gets in trouble from submitting reports to cross. We don't blame anyone. We're totally independent, and we're only interested in sharing the lessons that we learn from reports. It's a proactive system, so if we go back to that pyramid of risk, we're very much focused on the lower levels of that pyramid. It's almost an early warning system of what might go wrong, which gives us the opportunity to take some action to try and prevent the more serious incidents at the top of the pyramid. As I said at the very start, we're totally independent, and everything that we do is to act in the interest of public safety. But more reports are always needed, so if you have come across any safety issues, whether that be safety concerns or safety incidents that you think others could learn from, then please do submit a confidential report to cross. I like to think of cross as a community where everyone in that community is contributing to sharing and learning with each other. Cross wouldn't be anything if we didn't have people submitting reports to us, because we have nothing to share with our community. So if you've ever read a cross report and you found it useful, just remember that that was only possible because someone else just like you decided to submit a report to cross. So yes, if you have anything to share, please do send us a report. Or if you have any questions about the reporting process, then you can find our contact details on the website. So you can submit reports using our form on our website, and we also have an offline forum for people that don't trust the internet. Thank you very much. That's the end of my presentation.
Brilliant, thank you, Paul. I'll just switch to my screen now. Right, so we've got a few questions that have come in. We've got one, I'll start with a statement. So someone's just made a little statement. It's from Stuart. He said, "Excellent presentation, thank you. From my experience as a building engineer, it is worth subscribing to SCOSS and cross. Highlights issues you may not be aware of and focuses the mind on domestic and non-domestic structural issues." So we've got a question from Graham. "Although confidential, do you have problems getting information when investigating issues?"
So typically when reports come to us, because the person sending us the report is interested in sharing the lessons learned from that report, they'll have already done an investigation, and they'll be sharing the causes with us. So generally we don't have that problem. Sometimes we do get reports where maybe something's happened and the company's not quite sure why it's happened yet, and they're still doing their investigation. And in that case, we'll just tell the company, we'll just hold your report for now, and once you've done the investigation, if you can then share that extra data with us, and then we'll publish the report. So generally it's not really an issue, no.
Okay, so we've got a question from Colin. "Does cross cover radon gas?"
So I believe that's a contaminant in the ground. I can't recall any reports we have at the minute on radon gas. I think so I don't know about the effects of radon gas or anything, but if the effects could result in a safety issue, then we would accept a report on that. So if somehow radon gas in the ground, let's say for example it compromised the structural integrity of foundations, maybe it deteriorates reinforced concrete foundations or something like that, then that would be something that we'd be interested in, but I'm not aware of any reports we have on that. If you go onto our website, we have a little search box. If you type in the word radon, then you should find any reports that we have on that. But if you have any, please do send them to us.
So I've got another question from Roddy. Do you have to be a member of the ISE to access the reports?
No, our reports are freely available to everyone on our website, so there's no, you don't even have to register on our website or anything. It's just go onto our website and you see all the reports. I would highly recommend signing up to our mailing list, because we'll then send you emails about any newsletters that we publish. We only send 5 or 6 emails every year, so you're not going to get plagued with emails from us. One of our long-term visions is that, so at the minute we obviously have cross in the UK and other developed countries like Australia and America and Germany and Southern Africa. But our long-term ambition is that developing countries will also be able to use cross reports. So they might not have a cross scheme themselves, but they'll be able to go onto our website and learn from the cross reports. So that's why it's really important that we keep it freely available to everyone.
Brilliant. I'm going to have to cut us there, but I'll send the rest of the questions that I haven't that Paul hasn't answered over to Paul, and we'll be able to answer them outside of the session. I'd just like to take this opportunity to mention that the next webinar that's due in December is currently to be confirmed, and just to keep an eye out on our website, as we'll have something up there as soon as possible for the next webinar. If you've got any, the next thing is that our members community is now live on the website, which is fantastic news for all of our members. If you've got any questions or queries regarding how you set up your profile, please contact the team using the info@cbuilde.com email address, or give us a call on 01604 404 121. Our next training course at HQ is a course on boundaries. This course on boundaries will cover various aspects of the subject and will be useful to all who wish to embark upon the subject, or at least to have a knowledge of such when dealing with associated matters such as the Party Wall Act. So I'd just like to thank everyone for attending this morning's session, and I'd like to thank Paul for his very informative presentation. If you've got any feedback, please send that through to the info@cbuilde email address. We'd love to hear from you, and if you've got any ideas for another presentation or can do a webinar yourself, please do get in contact. With that, I'll wrap up. Thank you again, everyone, and thank you, Paul, and we'll see you online next month.
Thank you.
Thank you.